what people call negative logic. When we talk about negative logic, it means the opposite of. It don't mean it actually uses negative power supply. So you got to kind of be leery of some terms. It's just like the English language. You know, we got resume and resume. They're spelled exactly the same. So it depends on how you're using in a sentence, right? Left and left. So you can turn left, or you can be left behind. So that's the same word that has two different meanings. So when we talk about negative logic, we're talking about the opposite of the positive logic signal. So positive logic, we know we've got 5 basic gates. And what are the 5 basic gates? Yeah, let's do so we got an AND and an OR. How many inputs can an AND have? How many inputs can an AND have? At least 2. At least 2. So that's kind of a loaded question, right? You know, it's got to have at least 2, but how many could it have? Could have a lot, right? Y'all understand that? Biggest one I know of has 8 inputs. So what we're going to do here, though, is normally when we talk about them, we just draw the 2 inversions. So that's the symbol of what? And then we put that curve there, and then these 2 are curved, right? And what's this a symbol for? OR. Then we take the same symbol up there. This is a symbol of a D. Then we put a little bubble right there. And what's this? NAND. Then we use the same thing with the NOR. And then this guy right here is the, yeah, but we're talking about logic. We're not talking about the circuit. And that's kind of strange because the inverter is the only circuit that has a name. So this is not, right? That's a not. Everybody okay? But the name of the circuit is a what? Inverter. What's this? This is an AND. What's the name of the circuit? AND. So the not circuit, the not logic circuit, we call it an inverter. But the logic of form is AND. Now, when I come over here, we know this right here says all highs equal a high. So we come up here and develop a truth table, and this is why we're going to do this, because it's so easy to do it with 2 inputs, right? Because we know that the truth table varies with the square, 2 to the square inputs, right? So if we call the inputs A and B, and then we call the output X, then all we do is we know it's 2 inputs, so all we start doing is counting in binary. And what would I have for if I put 2 zeros on the input, or 2 lows? Huh? Okay. I'm going to come over and put this. What would it be? Okay. Put this. And 1. Okay. Everybody okay? Everybody okay? Now I look at that, and I see the AND is the unique function right there. So there's the AND. Okay, y'all understand that? And when we look at this, we say all highs equal high. So what would happen if any input is low? Well, I can't get a high. I mean, this is an any, this is an any, this is an any. When I look on the right, it's not a high, it's always a what? A low. Well, look what I just did. I took everything that was over here. Over here I said what? All. Over here I said what? Any. And then I just did what? I just made it the opposite, right? You understand? So over here I said any high, all highs equal a high. Over here I said any low equals a low. So y'all see, this is any low right here. A lot of people want to call that all lows, but if you do that, I'm going to correct you. That is not an all, that is an any. Why is it an any? Because the all is the unique. Which of this truth table, what is unique? The zeros are not unique, right? You understand? What's unique is the one. That's your alls, right? You understand? So when we say unique, we mean if we only have one output that gives us that. And that's when we use the term all. But for some reason, people want to call that an all, but that's not an all, it's an any low. Y'all understand that? Very important concept. You okay, Morris? Kind of looking. Okay, so let's draw this symbol. So anytime I say any, I'm going to draw this, right? I'm going to come up here and I'm going to draw this. Y'all follow me so far? Okay. Then I'm going to come over here and I'm going to look at the inputs, and the inputs are low active, and I'm going to put a bubble on the output.
So why you put the bubble on the input?
Because I say it's this guy is looking for what? Lows. So these are inputs over here. So these are inputs, right? You understand? And this right here is a what? Output. So over here I say all highs. So over here, when I look over here, I have no bubbles because I say what? High. Okay, then I come over here and I say high equal a high. So this is the input. So it says equals a high. So notice there's no bubble on the output. Over here I'm going to say all highs equals a what? A low. So since this says low, I put a bubble on the output. Since this says high, I don't put any bubbles on the input. That makes sense. Over here we say any low equals a low. Okay, so let's do a truth table for this guy. A, B, X. Is this any low?
Yes.
Okay. Is this any low?
Yes.
Is this any low?
Yes.
Is this any low?
No.
So what do you notice?
Same.
It's exactly the same thing. So we can say two different things about an AND gate. We can say all highs equal a high, or any low equals a low. Now we call this a negative symbol, negative. And what would this be? Would it be an or would it be a nor? Huh? Would it be an or would it be a nor? Why? Why is it a nor? I mean, when I look down here and I look at this nor, I see that the inputs are high active and the outputs are the low active. I come up here and I see this one, I see the inputs are high active and the output is high active. So notice up here, the active state of the input and the active state of the output are the same. I look down here and the active state of the input and the active state of the output are different. So this is a negative or. But the problem is people jump on the bubble on the output to mean NOR and NAND, and that's not true. What determines if it's a NOR and what determines if it's a NAND is that the active output is the active input, active state of the input compared to the active state of the output. If they're the same, it's going to be an or an AND. If they're different, it's going to be a what? A NAND or an OR. Do y'all understand that? So what we got here is we got two symbols for the same truth table. That makes sense. Two symbols for the same truth table. And all you do is just swap everything around. So if I come over here, so these are the same gate. When you buy them by their positive logic symbols. When you draw your circuit, you draw the gate for what the gate is looking for. And we'll look at the schematics in the back of the book here in a second. So if I come over here and look at this one, what am I going to say? I'm going to say any high equals a high. Well, I'm going to turn that around. And over here, I'm going to say all. Over here, I said high. What am I going to say over here? all lows equal a low. This would be an OR. This would be a negative and. Good. Because we said all. When I say all, it's an and. When I say any, it's a what? It's or. Let's draw the symbol. So I'll come up here and I'll do this. That's supposed to, I say what? Any low equals a low. So if I come over here and did this truth table, I'm sorry, I said all lows equal a low, excuse me. If I do the truth table on this one, A, B, X, is this any low? Is this, I'm sorry, any high equals high? Is this any high? Okay. Is this any high? Okay. Is this any high?
Yeah.
Okay. Is this any high?
Yeah.
Is this all lows?
Yeah.
Is this in, so look what I'm talking about.
All those.
Yeah, is this all lows? Is this all lows?
Yeah.
So over here it says what? All lows equal a low. So that means this truth table and these truth tables are exactly the same. One of them is the positive logic symbol. One of them is the negative logic symbol. But the truth tables are the same. They are the same gate. Y'all understand? Okay. Now, why do we want to do that? Why do we want to confuse this? Well, we're not confusing it. We're making it simpler if the circuits are drawn correctly. Sometimes this guy might be looking for this to work, to make something work. Or it might be looking for this to make something work, right? You understand? So what you do is you draw the symbol that is of the logic function it's serving in the circuit. Let me see if I can get this. Like I said, I've updated. I had to do a restore. And I don't know if my camera's going to work. Let's see. I think I got a footprint. So let's see. Camera plus VGA. No, that's not what I got. This is what I got right here. Okay. Come on, come on, come on, come on, come on, come on. If it don't work, well, let's think we're getting something. Okay. So what I want y'all to do is I want y'all to mark this page. We will be back. Turn all the way back to page. And mine's going to be upside down. Like I said, I didn't know. I can turn it around, but not right now. So I'm back in appendix. Now let me turn my book upside down. That would probably be better because I can see it better now. Okay. So on page 934, and this is a drawing of a computer. By the way, this is a microcontroller, but this is a picture of a computer. This is a schematic of a computer. And what we're doing is we're looking at this guy right here. Now this is an AND gate. If I went out and bought this thing, I would buy an AND gate. If I look at, well, we know what a 74HC04, that's a quad 2 input AND gate. But it's not drawn as an AND gate, right? You understand? I'm 74HC08 because the 7400 is an AND gate, but the 74HC08, this is the one of the first guys we're going to use. This is an AND gate, but they got it drawn as a negative NOR because what this guy right here is looking for is it's not looking for a high, it's looking for a low. That's what it needs. And what does this say? Well, this says any low will give me a low. Right? You understand? So I don't have to figure, if this was drawn as an AND gate, then I would have to figure out what it's looking for. I'd have to figure out what this guy's looking for, right? You understand? But it's drawn that way. I look over on the next page. So this is 135. So this right here is an OR gauge. If I looked up a 7432, it's going to be an OR gauge. But they don't have it drawn as an OR gate. They got it drawn as a negative AND. Because this guy right here, this CS, is looking for a low. Well, what does it need to get a low? Well, it says all lows equal a what? Equal a low. So what we're saying is that if the person that draws the schematic switches between positive and negative logic symbols, the symbol is going to tell you what it's looking for. Later on, we used to do a component level troubleshooting class on a compatible computer. That's back when they cost about $2,000 or $3,000 a piece, so you could afford to fix them. And this was before everything was integrated. So now you look at a motherboard, you know, you're going to see the microprocessor and a couple of big chips out there because everything has been around so long, it became so standard the way things were that they just did what? They just started integrating. In fact, your cell phones are basically the same. About the only thing they do now is change the processor out and put more memory in. So if that's all they do, then what can they do? Well, they can put everything that runs the phone on a single integrated circuit because it all does the same thing, right? You understand? Oh, we had one on the video card where everything was drawn in positive logic. And what did you have to do now? Well, you have to figure out what the circuit's looking for. And of course, all the other prints are in what I call active logic. That's Rich's name. I have never seen a name for it, but active logic is when they draw the symbol depending on the active state that's needed to make that circuit work, right? You understand? So what would this be? Well, this is a 74HC08 again, so that's an AND gate, but you don't go on mail order and find a negative OR. You can't find them because when you buy them, they're sold by their positive logic symbol. Y'all understand that? But negative. So if we switch, but here, let's find another one. Oh, that's negative logic. It's negative logic again. Here, this is 396. This is the 7430 that I was telling you about. This guy, oops, sorry guys. Yeah, so this is the 74 LS30. This is an 8 input NAND gate. So this guy is drawn as a NAND gate. So this guy is looking for all highs to get a low. You okay? 339, I'm on page 339. By the way, this is see this guy right here, we'll talk about these later on. What did I say? 939. Y'all have to understand, my book is upside down. My book is upside down. This gate right here, we'll talk about later on. The problem is, on these guys, what's a legal high? What do we consider to be a legal high? And above, right? And what do we consider to be a legal low? About 400 millivolts. Between 400 millivolts and 2.4 volts, we don't know. It's going to switch somewhere, right? You understand? But we don't know where it's going to switch. We know we guarantee a switch if we put at least 2.4 volts on that input. We're guaranteed for it to switch. If we put less than 400 millivolts, it's guaranteed to switch. These guys right here have a special input on them. These are called Schmitt triggers, and they trigger at a spot. So they'll recognize it as a low until it gets up to a certain voltage. And as soon as it crosses that voltage, it switches. They recognize it as a low as soon as it drops below a certain voltage. And if it sees it as high, the input can meander around all day long, and it'll see it as a high until it goes down to the lower threshold. So these are called Schmitt triggers. Notice it's still an inverter, except this guy has no invalid. These guys have no invalid states. The inputs, there's no invalid input on these guys. All you have to do is exceed an upper threshold and a lower threshold. This is called a hysteresis curve symbol, by the way, which means they're not the same. So the high threshold is not the same as the low threshold. Does that make sense? So the high threshold might be 2 volts, and the low threshold might be 1 volt. So if it sees it as a low, it's going to keep seeing it as a low until it gets above 2 volts. And then it's going to keep seeing it as a high until it gets below the lower threshold. So this is called a hysteresis loop. It was originally developed by magnets. When we magnetize a material, when you magnetize it, how much energy does it take to magnetize it in the opposite direction? And it came up with this thing we call a hysteresis loop. So that's this guy right here. See the little symbol right there? Normally we use these things on digital logic circuits that's getting information from the outside world, because you can understand that those signals meander all over the place. So these are called Schmitt triggers. But see the difference. So here they needed all highs to get a low. By the way, here's the 2764s. These are the ROMs. These are the read-only memories right here. Where's the RAM? Here's the microcomputer chip right here. So this is a microcomputer. It's not a microprocessor, it's a microcomputer. So a microcomputer chip, these are actually ports right here. That's what the P stands for. So these are I/O ports. You don't see the address buses that we looked at. 62128, this is a RAM chip right here. And you can see all the address lines where we actually select locations. Here's the data lines. This is the data bus we talked about. This is the address bus that we talked about. I remember that when we gave you all the brief layout of a computer. Here's the control bus right here. This is control. And so this is RAM right here. This is ROM. What else? This is an ORS-232 interface right here. And then this is the chip that actually handles that. This is the clock generator on page 938, if I don't read it upside down. So this is the clock generator. This is a symbol of a crystal. A crystal is a device, once you excite it with DC, it oscillates at a precise frequency. Thank goodness we wouldn't have watches if we didn't have these things. And then it feeds this into a Schmitt trigger. This is the automatic reset. We'll talk about that later. No, that's not a crystal. That's a capacitor. Strong little different. This is automatic reset circuits, what it is. So this is what would reset the computer, like when you turn it on. It's pretty neat. Well, you know, computers, when we turn computers on, somehow we have to tell them to go into read-only memory and start running programs. So one of the pins on the control bus, here's this processor right here, is one called reset. So whenever this reset, and see it's got a little bubble on it. So every time this reset goes low, it tells the processor to go to a certain address in ROM. Okay. Well, so that means if I looked at this, so you got a sequence on your phone that you can press and actually reset the processor. I think on the iPhones, you hold down this and hold down this for a while, and it will reset. Which means it'll go back to its original ROM location and start running its program. So if you ever get this sucker that locks up, and it locks up just like these computers, it locks up. These they don't have resets on them, so what you do is you unplug them and pull the battery out. And then when you plug it in, it does an automatic reset with this little circuit right here. This little circuit right here is a capacitor. It charges. So when it sees the power supply come on, the capacitor starts charging. When it gets up to the threshold of the Schmitt trigger, it automatically generates a reset for the computer. So this is what resets the computer when you turn it on. These guys have a reset button. So this is, if you open up these doors and look, there's a reset button on desktops. Desktops usually have a reset button. Well, there's the button right there. When I press that button, it discharges the capacitor. And then when I let it go, it lets the capacitor start charging. And as soon as it hits the threshold, it generates a reset. So this would be you resetting the computer. And then, of course, if you turn it on, and when the power supply comes up, it does an automatic reset. And that tells the microprocessor, no matter where it's at, to go back to the ROM memory and start running what we call We call it the BIOS. I don't know if you've heard that term, the basic input-output system. That's the programs that gets the computer born. That's like your automated nervous system. So when you're born, you have ROMs, right, in your brain. So as soon as you're born, you start running programs. And they were there to start off with. And then, and that would be our BIOS. It would be our automated nervous system, which would be, it's the one that makes us walk. Our heartbeat, it allows us to see. We don't have a program. It was built into us to be able to see and breathe and get rid of waste, right? We get rid of waste. But what I wanted to show you, even though we got off on a tangent here, these are drawn as NAND gates. Because why? Because they're looking for all highs to get a low. So whatever's down this line right here needs a low for it to be true. So what we're saying is that we have two symbols for every gate. We have a negative logic symbol and we have a positive logic symbol. What determines which symbol you use is dependent on what function the gate has in the circuit. And you get draftsmen that draw all positive logic. We had bought some inverters. Basically, an inverter was something that took DC and converts it into AC. Y'all probably heard of the term before. You can buy inverters for your car. But this guy was probably about 6,000 amp circuit. And it was controlled by a digital circuit. And the draftsman, whoever drew it, must have only had one template because every gate was an OR gate. And we started looking, we said, ain't no way in the world this sucker's going to work. And then what we did is we started looking up the part numbers and found out that they were ORs and ANDs and all kind of gates, but the guy drew everything as what? As an OR gate. The whole schematic. All these logic circuits. Couldn't you imagine if somebody drew all these as OR gates? Trying to figure that out, and it was a challenge. So we had to literally look at the part number on every IC. So we had the circuit board, and we'd look up the U number. We would find it. We'd look up the part number on the IC and figure out what it was, and we had to redraw all those prints. It's almost as bad if they draw everything in positive logic, because then what do you got to do? You got to figure out what the gate's looking for, because it can either be looking for its positive logic function or it could be looking for its what? Negative logic function. So let's start back and let's just see if we can do these gates. So what do? We call it complementing the gate, which is the opposite of. So let's go. Let's see if we can do the symbols. The truth tables are the same. So here's the positive logic symbol. Sorry. I guess I should have just started from scratch. We're worried about the Boolean equation later on. So this was an AND gate, right? Which says what? All highs equal a high. The negative logic, on negative logic, your inputs will always be low active, right? So I'll change everything around. Over here I said what? All. Over here I'm going to say what? Any. Over here I said high. I'm going to say what? Low. Okay, then I'm going to put equal to what? Low. Which would be any, right? Low equals low. What's the difference between those gates? Nothing. They're the same thing. It's a two-input AND gate. It's just how you draw it and how you interpret it in a schematic, right? You understand? So what do we say here? Any high equals a high. So what am I going to say over here? All good. Lows equal a low. So the symbol, all lows equals a low. This would be a negative. What? And. Why is it not an and? Because the active state of the input and the active state of the output are the same. It's not the bubble on the output. So what does this gate say? All highs equal a low. So over here I'm going to say what? Any low equals a high. any low equals a high. Negative,
Or,
not an or, nor. Y'all understand this, right? Yes or no? If the active state of the input and the outputs are different, so what's this? And this is low active on the input, it's high active. That's going to be a NAND or an OR. If they're the same, it's going to be an AND or an OR. Except I'm going to say negative. So why do we call this a NAND? Not because it's got a bubble on the output. That's not why it's a NAND. It's a NAND because the inputs are high active and the output is low active. So is that the same? No. So don't get that bubble on the output as being NANDs and NORs and that kind of stuff, right? You understand? It's what we're looking at is the difference. If they're the same, it's going to be a what? An AND or an OR. Or if they're different, it's going to be a what? An AND or an OR. But for some reason, people grab on that, unfortunately. What would I say here? Any high equals a low. Now this is a NOR. Why is it a NOR? Because there's a bubble on the output? No. It's a NOR because the inputs are high active, the output is low active, right? So over here I'd say what? All lows equals a high. Oops. All lows equal a high. This is a negative NAND. So what am I going to do over here? Over here we would say high equals a low. Over here we're going to say a low equals a high. And we draw the symbol like this. So you're going to have to switch a knot. A knot's a knot, right? But we say it differently. So over this guy's saying, okay, I'm looking for a high to get a low. This guy's right here saying, I'm looking for a low to get a high. And we call this a what? Yeah, we call this a negative knot. We call this a knot. So its name don't change. We call this a NAND. And this is a negative NOR. We call this an OR. Negative AND. We call this an AND. Negative OR. There's our 5 basic gates. We don't have 10 gates. We got 5 basic gates, but each gate has got 2 symbols. One of them's a positive logic symbol. One of them's a negative logic symbol. So what do y'all think? And man, once you catch on to this, once this clicks and you get into a schematic that's drawn right, then you can figure that sucker out. You don't need truth tables. You don't need anything. You don't need Karnaugh maps. Karnaugh maps and Boolean algebra is neat. We'll look at it a little bit, but that's more on the design side. So what we do with Boolean algebra and Karnaugh maps is that if we can come up with a circuit, if we can develop an equation for that circuit, a Boolean equation, or then we can, and if it reduces, then that means the circuit's reducing, right? You understand? So that's more of a design. We don't teach design in this class, so when we get into Boolean algebra, we'll touch on it. We might take one night to do the whole thing in Boolean algebra. When you do the labs on Boolean, you'll still do the labs on Boolean algebra, but I've reduced them for you. So what that means is you'll wire the circuit one way, and you'll develop the truth table for the circuit, and then you'll wire it reduced, and you'll do the truth table for the circuit, and you'll find out they're exactly the same, which is what's so neat. And it'll give you a feel of the power of these logics. Karnaugh maps. Boolean algebra, a math equation can be just about any length, and you can reduce it. Karnaugh maps deals with, it's very similar to a truth table, but you set up a table. But if you got 4 inputs, then your table is going to be 4 by 4, which means 16 blocks you got to figure out. So that means it's just like a truth table. You know, once you get past 4 inputs, Karnoff maps basically turn into being useless. And so I prefer Boolean algebra because that's what I learned and that's what I do. Karnoff maps are fun because they're graphical, I guess. But like I said, we'll just look at that just a little bit. But this is important right here because now we can and we'll show y'all. So over here, if I did the Boolean equation on this, I'd say X, and then I'd say A and B, right? You understand? What would we say here? X equals to what? A or B. What would I say right here? X equals to A and B. And then I put a bar above it. Y'all follow me so far? Over here I'd put X is equal to A or B. I'd put a bar above it. And here I'd say X equals to, some people put not X, that right there. Right? Okay. So what would the Boolean equation be for this guy? X equals to A or B. Now what we do, if the inputs are low active, we put a bar above each input. If the output's low active, we put a bar above it. Now this is not a double negative. This would be a double negative. So if I was doing Boolean and I ended up with this, that would be a double negative, and then we would turn that into a positive, right? You understand? Or if I was doing Boolean algebra and I came up and if I was doing the Boolean algebra and I came up with this, and then that would be a double negative, and that would turn into a positive. But this is not a double negative, right? You understand? Yes or no? So that means these don't cancel each other out. All right, guys, so what would this be? So y'all help me. So I'm going to start off with X. I know I'm going to come over here and I'm going to put A and B. What would I do now? Are the inputs low active? Yes. So I'd put a bar above each input. Is the output low active? I'd put a bar across the whole thing. Y'all understand that? Over here, what would I put? I'd put X is equal to A or B. What would I do? But not a bar across the whole thing, right? Y'all understand that? What would I do for this guy? And B, and then I would do that. What would this guy be? It just swaps around. By the way, this is the only thing, this is the only time it's legal to put a negative on the left. It's for that equation right there. So these are 10 basic gates. Now what we're going to start doing, we're fixing to go to lab. What we're fixing to do, what we're going to start doing is that we're going to take these 5 basic gates and then we're going to start combining them into circuits. We call them combinational logic. So combinational logic circuits consist of the 5 basic gates. So when we start talking about counters, when we start talking about multiplexers, when we start talking about encoders and decoders and parity generators and all this kind of stuff, all those combinational circuits are made out of the 5 basic gates. So this is the basic of all logic right here. All digital logic is just 5 basic gates. If I do math, I do it with these 5 basic gates. So if I came up with a circuit that could add binary numbers, then that circuit is going to be made of what? These 5 basic gates. And eventually we're going to split away from them because the circuit gets so complex that we can't do it. So like counters and stuff like that, we'll look at them, but we're not going to try to figure out how they work. Because all we're going to do from now on is we're still going to run into these by themselves, but a counter is a counter. If you know what it does and you know it's made of the 5 basic gates, then we don't have to draw the whole internal circuit just to figure out how it does, right? So we'll do it on encoders and decoders because sometimes those are still done with discrete logic. I mean, if I've got 4 of these inside a single chip, and I need another circuit, then I'll do the combinations, and I only need one of these. That's going to leave me what? That's going to leave me 3 more that I can do something with. So I'm not going to come in and put a decoder chip in there if I can use those 3 to do the decoder that I need to do. So, you know, a lot of times it ends up, so we'll look at some schematics, and you'll see they'll have a thing called spare gates. And these were the gates that they just couldn't fit in. So, you know, if you got 6 gates inside an inverter and you only need 3, then you're going to have to use it. That's the only option you got. That leaves you 3 that just go unused unless you can find a use for them, right? And we'll show y'all what you do. TTL is pretty forgiving about leaving gates in there set up but CMOS, we'll show you that too. Them suckers will switch on anything. So what we'll show you, what y'all need to do, either tie the unused inputs up or tie them down. So any questions on this? Ask them now. So now we're moving into that whole sheet, right? You understand? So everybody's got that sheet. Huh? Yeah. What the other side is, and you got to match these too. I mean, you got to know that these 2 gates right here are the same. They are the same. It's the 2. We have 2 symbols for the same circuit. One of them we call positive logic. One of them we call negative logic. So these are positive logic, and this over here is negative logic. So y'all need to start working on those and memorize, because eventually on a test, you're going to have to draw all this out. Basically what I got up here. I say draw the symbols of 5 basic gates. I say draw the negative and positive symbols, and I say they have to be beside each other. You get people have all that problems. They'll put an and over here they think they got to put an and over here because it's an and on the left. Huh? That's wrong. That's wrong. So what we'll do is we'll give you all a little worksheet. It's not very hard. What y'all do, it's just a grid, and it's one of these things where you match, where you draw lines, where you match negative and positive gate symbols. But I guess we got a few people that didn't show up. Kyle, Mary, and Keith, right? And Kareem came in late.
Yeah.
Oh my goodness.
Yeah. Yeah, and that's what I think too. That's what, like, everybody started crying.
What was the wreck at?
I think I was a commission of from 459.
Oh yeah, I heard about that on the radio.